So this is that one example that if we try to evaluate, we want to try to evaluate this integral over the rectangular system. Well, suppose we want to evaluate this integral first with respect to y. There's no way we can evaluate this one, unfortunately, because if we set u equals to x squared plus y squared, du with respect to y would be 2y dy. However, do you see we're missing a factor of y which stands the u du part? So here is where Polar is going to simplify the problem, or actually is going to give us the tool to move on through this. So number one, well, before computing the integral, let's analyze what are we really doing, so let's see. So we have our Cartesian plane, and number one, these limits of integration for the inner integral, which tell us the variation of the y in this case. So this is telling us that y varies between 0 and the square root of 9 minus x squared. From here we can deduce that y is less than or equal to the square root of 9 minus x squared, square both sides, y squared less than or equal 9 minus x squared, and essentially this is x squared plus y squared less than or equal to 9. So essentially this is all the points inside of the circle, and actually not the whole circle, just the upper part of the circle, because we only have the positive square root. If we had both the positive and the negative, then we would be considering the lower part of the lower semicircle. So that's for the variation between the y's. These limits of integration for the outermost integral, which is the dependence for x, they're telling us we're going to go from -3 to 3. All right, and I mean that's actually a circle of radius 3, so it should actually complete this idea. All right. So let's change this to polar coordinates. So number one, so for polar coordinates, we know that x squared plus y squared equals r squared. All right. Now, what else? We need to change this dy dx into r dr d theta. All right. And thanks to that factor of r, this function will be integrable as opposed to the one that we had before. Now, we need to be careful with the limits here. So that's a sine r squared, dy dx becomes r dr d theta. Well, in this case, for the innermost, so for the radius. So for the radius, we go from the very center, which is radius equals to 0, to the outermost, which is 0 to 3. But in this case, for the angle, since we are only looking at the upper semicircle, this is varying from 0 to just pi. All right. And now, thank you, polar coordinates. We got a factor of r that will help us set up the u du part. All right. So, so u equals r squared du equals to r dr. So r dr equals 1/2 du. And well, so that's going to be the integral from, how about we also change the limits of integration to avoid doing the back substitution for r squared? Well, so u of 0 and u of 3, that's going to be 0 squared, which is 0, and 3 squared, which is 9. So those limits are going to be changed I will change to, well, number one, 0 to pi, and for the second integral, 0 to 9 of sine of u, and that's a 1/2 du and d theta. Don't forget about the d theta. So let's integrate sine. What's the integral of sine? Isn't it negative cosine? So that's going to be the integral from 0 to pi. And then the integral of sine is negative cosine. Let me write the cosine of u evaluated from 0 to 9. And this factor of 1/2, I'm going to write it outside along with the negative sign, which comes from integrating the sine function. So don't forget our d theta. And in this case, well, the numbers are just going to be, we're going to leave them like indicated without computing them. So that's going to be cosine of 9 minus cosine of 0.
It's a 3, right?
Which one?
Cosine of 3.
Cosine, oh, but we changed the limits of integration.
Oh.
Yep. I mean, we can go back, substitute r squared, and then plug them like this. We're going to get the same anyway. And that's a d theta. And so, well, cosine of 0 is just 1. Cosine of 9, let's leave it as cosine of 9 since that's not going to give us an exact value. So, and actually, so that's cosine of 9 minus cosine of 0, which is 1, d theta, and 0 to pi. This cosine 9 minus cosine 9 minus 1, it's just another multiple constant that we can take outside of the integral. So that's going to be negative 1/2 cosine 9 minus 1 integral from 0 to pi d theta. And what's the integral of d theta? Isn't that just theta? So that's a negative 1/2. Well, so it kind of freaks me out when I get a negative number for an integral for which we are potentially finding a volume or an area, because that will make me think that we're getting a negative result, which we're not supposed to get negative results for this type of problem. So I'm going to use this negative sign and reverse the order of these two terms to get a that looks more like a positive answer. And actually, cosine of 9, I mean, the largest value of cosine is 1. So cosine of 9 has to be a tiny number. So yes, it's going to be a positive number. So that's theta from 0 to pi. And well, so that's 1/2. 1 minus cosine of 9. And pi minus 0, that's simply 1 minus cosine pi. You can distribute the 1/2, or you can have the pi multiplying in the front. I mean, different ways to express the same thing. All right, so this is the exact answer. All right, and that's example number 5. Wait a minute. Oh, here it is. Number 3. For the next example, okay, so they're asking us to find the volume of the solid bounded by the plane z equal to 0 and the paraboloid z equals 1 minus x squared minus y squared. Well, this paraboloid is going to be opening upside down, and we can tell by the signs of the quadratic terms, you know, as an analogous to what we'll be seeing in two dimensions. For example, 1 minus x squared, it's basically an upside down parabola. So in 3D, it would be an upside down paraboloid. So, all right. So what do we have? So we looked at the solid on Desmos, and so this will be, let's look at the projection in the xy plane. So essentially, we have this circle of radius 1, all the points that lie inside the circle of radius 1. All right, so in this case, to find that total volume of to find the volume, we will need to look at the intersection between these two solids actually. So we set up z equals to 0 and set it equal to 1 minus x squared minus y squared. And again, we'll have all variables on the left. And well, that's what takes us back to that unit circle, which is the projection of the solid in the xy plane. Alright, so we did it in Desmos first, but now this is the algebraic justification of why is this a unit circle. So let's see, what else? Now, so we want to find the volume here. Let's set up the volume, that is V equals double integral over the region R of some function f of x y for now, dA. However, we don't want to evaluate this over the world of xy, but rather over the world of r theta. So let's see. We need to convert this z equals to 1 minus x squared minus y squared. So that z equals to 1 minus x squared plus y squared. And what's x squared plus y squared in the world of r theta? R squared, right? So that's z equals to 1 minus r squared. So f of xy, which will become an f of r theta, well, that's going to be 1 minus r squared. And dA becomes r dr d theta. Well, so that's the setup of the integrand. That's the function that depends on r and theta this time. Now let's look at the limits of integration. Well, so the innermost integral is to compute the radius variation in this case. So if we look at this region of integration, r varies from 0 to 1, right? Because it's all the points within the unit circle. And well, since in this case, again, they're not telling us only the upper half, the lower half, or just the first octant or the first quadrant in the 2D perspective, well, that means it varies from 0 to 2 pi. All right? Now, let's see. Let's evaluate this integral. Well, this one is going to be fairly easy because it's going to involve just general power rule. So let's distribute. So this will be the integral from 0 to 2 pi, integral from 0 to 1. So that's r minus r cubed, dr d theta. Well, so we can go about the integration with respect r. So that's going to be the integral from 0 to 2 pi. And the integral of r, that's r squared over 2 minus r to the 4th over 4. And that goes from 0 to 1 with respect theta. Applying the fundamental theorem, I mean, that's going to be 1/2 minus 1/4. And evaluating at the lower limit, isn't it just going to be a big 0? Okay, so this will be the integral from 0 to 2 pi. So that's 1/2 minus 1/4. Well, what do we get? That's 1/4. And we can take out the 1/4 outside of the integral. And that's 1/4 times theta going from 0 to 2 pi. And 1/4 times 2 pi minus 0, that's going to take us to pi over 2. So that's the volume of that piece of solid. In this case, bounded by the plane z equals to 0 and above by this paraboloid. Okay? Let's do the next one, number 7. Find the volume of the solid that is inside the hemisphere z equals to 16 minus x squared minus y squared, and outside of the cylinder x squared plus y squared equals to 1. Yes. Briefly describe. So we have these couple of these two circles, the circle of radius 1 and the circle of radius 4. And we can start already setting up the integral to find the volume, which is double integral over the region R, f of x y for now, dA, but we're going to change this to the world of r theta. F of x y is going to become f of r theta, which in this case is our square root of 16 minus r squared, r dr d theta. And again, if we were to evaluate this integral, let me take a quick side trip. So that's 16 minus x squared minus y squared. So if we wanted to evaluate this integral, whether dy dx or dx dy, it doesn't matter. Do you see the problem here? We wouldn't be able to evaluate this integral in pink right here, because whether we start with dy or dx, when we set up a u substitution, we need again another factor of x to set up the u du part, and we don't have that. However, the theta is going to bring us that factor. So let's set up a u. Oh, before setting up the du, let's look at the limits of integration. So r for the innermost integral, which is over the radius. So r varies between 1 and 4. And the angle for the outermost integral, that varies between 0 and 2 pi. And again, unless otherwise stated, like we want the volume only for the upper part or one side, well, so in this case it's the whole thing. So u equals 16 minus r squared, du equals negative 2r dr, and r dr equals negative 1/2 du. Alright, and well, let's change the limits of integration to avoid back substituting long expressions on radicals. So u of 1 and u of 4. So that's 16 minus 1 squared, 16 minus 4 squared. So that's going to be 15. And, well, 16 minus 4 squared, which is also 16, isn't that going to be 0? So let's write down this integral, at least the innermost integral, from 0 to 2. So it's integral from 0 to 2 pi. And then the inner integral becomes from 1 to 4 to that from 15 to 0. And again, we're seeing this lower limit to be larger than the upper limit, but don't worry, did you see this factor for the du? It's negative. We can use that property of integrals to reverse the order of the limits of integration by just changing the sign. So that's going to be the square root of u times negative 1/2 du. And well, this is the same as saying the integral from 0 to 2 pi, that's the integral from 15 to 0. And so that's, well, no, never mind. U to the 1/2, negative 1/2 du. And, well, we can integrate u to the 1/2. That's going to be u to the, well, you know what? Let me get rid of the negative and change the limits of integration from 0 to 15. So we don't do too many operations afterwards. All right. So let's take out 1/2. And that's u to the 3/2 over 3/2. And that gets evaluated from 0 to 15. And don't forget about the d theta. I forgot it here. I forgot it there as well. All right. So, okay, dividing by 3/2. Isn't it the same as multiplying by 2/3? But when we do that, check this out. Let me do this on the side. So this 1/2 multiplying by the reciprocal, which is 2/3, the 2's cancel, leaving us with only 1/3, right? So that's the integral from 0 to 2 pi, and that I'm going to take that 1/3 outside, and that's 15 to the 3/2 minus 0 to the 3/2 d theta. Well, this is just a constant. It's just a constant factor. But now this 15 to the 3/2. Let me write it on the side again. This 15 to the 3/2 is the same as saying the square root of 15 cubed, or the square root of 15 cubed. Well, the latter one since the number 15 it's not a perfect square, we cannot do this one to then cube it. So instead, I'm going to work with the 15 cubed as a 15 squared times 15, and then take out the the perfect square. So that's 1/3 integral from 0 to 2 pi. So that's the square root 15 squared times 15 d theta. And well, the square root of 15 squared is just 15, and well, that's 1/3 times 15 root of 15 integral of d theta from 0 to 2 pi. And we can already integrate the d theta. 15 over 3 is that a 5, and theta, which varies from 0 to 2 pi, and 15 root of 15 times 2 pi minus 0, that's essentially upper limit minus lower limit.
Should be 5.
And yes, right. And 2 pi times 5, that's a 10 pi root of 15. Right? Question?
Shouldn't there be like a negative in there somewhere?
Oh yes, so this negative right here that we had from the u substitution, I use it to reverse the limits of integration from 0 to 15. That way we don't do too many operations like taking the constant outside and then do the integration and then reverse the limits. So I did everything in one shot here. All right, what's next? What's the next one? So use a double integral to find the area enclosed by one loop of the 4-leaved rows R equals cosine 2 theta. Remember those from Calc 2? Finding areas of petals of flowers and cardioids and all those. Those are coming back. Yes. All right. So number 1. Okay, let me go and plot R equals to cosine 2 theta. I need more zoom. Number 6. No, zoom standard or zoom fit, actually zoom fit. All right, so that's our 4-leaved rows, right? And they're asking us to find the area of only one loop. Only one petal rather. Okay, so let me draw the graph over here. And all right, sort of, right? Okay, so they want us to find the area of only one under one single loop. That is from here. Well, so in this case, we need to figure out the limits of integration ourselves. They're not telling us directly, from this angle to that angle, the radius, blah, blah, blah. No, they're not telling us anything. And this is actually an area problem, not a volume problem. So let's set up area. Let's write down area equals to double integral over R dA for now. All right, we're going to start from here, then we're going to change this to R dr d theta. So that's the double integral. Let me leave some space. R dr d theta. How do we know this integral is going to describe area? Remember, whenever we have a double integral, if the integrand right here is an indivisible one only, that describes area. Alright, so in this case, how do we find the limits of integration? So essentially, to go about those limits, see how this loop goes in this direction, goes around, goes back to the origin. So the limits would be whatever angles are these. Alright? So we need to figure out those two angles. So, and notice how to get to these angles. That's when, suppose there's a particle going around that trajectory. That's always at the origin, right? So in this case, we need to set this cosine theta, cosine 2 theta equals to 0, we need to figure out when it's that equal to 0. Well, we know that 2 theta equals to 0 for, okay, when cosine, for angles like pi over 2, 3 pi over 2, 5 pi over 2, etc. Right? So cosine is 0 for those angles, but in this case we don't want to find for theta, but actually for 2 theta. So divide both sides by 2. Theta equals pi over 4, 3 pi over 4, 5 pi over 4, etc. Well, that's initially the solution to the equation cosine 2 theta equals to 0. Well, so if we do this, from the picture, this is the pi over 4. So initially, by just looking at the picture, it seemed like a pi over 4, but we needed to solve the equation to verify that indeed this is pi over 4. So if we do these limits pi over 4 to 3 pi over 4, we may run into a situation in which we will do this same area minus this essentially negative area, we will get a 0. So, and I know this because we've done this before, and we did this back in Calc 2, and we needed to redefine the limits of integration, or the whole integral rather, so we don't get that situation. So instead, well, another choice is to go negative pi over 4. How about that? So we don't go these limits. Well, so one possibility here is, okay, so the radius varies from, okay, what about the radius? How is the radius varying? So from the origin to any point, all right, to any point, these rays are going to point towards whatever function is in this case, in accordance with the function cosine 2 theta. So from the origin, which is 0, to cosine 2 theta. However, what about the radius? I mean the angle. So one way to express this integral to get the entire area is to go from negative pi over 4 to pi over 4. Now, since we've done this before in Calculus 2, we got into a situation in which those two areas cancel out, because one area is above the x-axis, the other one the x-axis, below the x-axis, so basically they cancel out. So it doesn't make sense to get an area equal to 0 when we are clearly seeing that there's an area there, right? So there's two things. Number one, to fix that issue, we redefine the outermost limits of integration, which is for the angle. And the advantage of that is because we would be taking advantage of the symmetry of this shape. So how about we just find the area, the upper area, and whatever we get for the upper area, just multiply by 2. All right? So instead, we will go from 0 to pi over 4, from 0 to cosine 2 theta, r dr d theta, and this result multiplied by 2. Right? Let's multiply that by 2. So this will be, let's compute the integral. That's 2 times the integral from 0 to pi over 4, the integral of r dr d theta. Isn't that going to be r squared over 2? And r goes from 0 to cosine 2 theta d theta. Evaluating upper limit minus lower limit. Let me check how these two, actually, check this out. These two cancel. One is in the numerator, one is in the denominator. So the more we can simplify, the better as we go. And well, from here, this will be the integral from 0 to pi over 4 of cosine squared to theta minus 0, right? D theta. And well, to compute the integral from 0 to pi over 4 of cosine squared 2 theta. Again, we cannot use a u substitution if we said u equals cosine, because we would need a factor of sine multiplying with the d theta in order to go about that integral. However, trigonometric identity. So we already used the power reduction formula for sine in a previous problem. We're going to use this time. Okay, I'm going to make a mistake on purpose to see if you can catch it. So that'll be the integral from 0 to pi over 4. Huh?
So it should be minus?
No, the sign is fine. Was that?
The sign would be negative, but since it's cosine, it's positive.
Yeah, so the sign is fine. But exactly, it has to be 4 theta, right? Because, so when we use this power reduction formula, every time we've used this power reduction formula, the angle gets duplicated, right? We double the angle. So if we had a 2 theta, that has to become 4 theta. All right? And well, so that's 1/2 1 plus cosine 4 theta d theta. And we can go about writing a couple of integrals. Number one, 1/2 the integral of d theta from 0 to pi over 4. And 1/2 the integral of cosine 4 theta. And well, the integral of d theta, that's well 1/2 theta plus 1/2 the integral of cosine, which is sine 4 theta from 0 to pi over 4, but I left a space over here for that 1/4 that comes from the integration of cosine 4 theta. That's going to give us the following value. So that's 1/2 theta plus 1/8 sine 4 theta from 0 to pi over 4. Again, upper limit minus lower limit, as usual, fundamental theorem. So that's 1/2 pi over 4 minus 1/8 sine of 4 times pi over 4, and then minus, well, again, if we apply the lower limit, which is 0, that's going to get zeroed out. 4 times 0 is 0, sine of 0. Can we just go about a big 0? And well, again, oh, these 4's cancel, leaving us with a sine of pi. What sine of pi as well? Isn't it also 0? So final answer, pi over 8. Let's do the last example for this section. Write an iterated integral in polar form to represent the area of the region in the first and fourth quadrants outside of the circle r equals the square root of 2, and inside the Leibniz gate r squared equals to 4 cosine 2 theta. All right. So, well, without getting into too many details, let's get to the graphs. Well, technically, we would have to draw the graph of r equals plus minus the square root of 4 cosine 2 theta. So that means plus or minus 2 square root of cosine 2 theta. Okay, let's go to the graphing calculator. So let me clear everything we have. So that's a negative 2 square root of cosine 2 theta. Close parentheses, and the positive counterpart 2 second square root of cosine 2 theta. Okay, so let's graph. Well, unfortunately, it's not going to give us the entire graph, so let's do zoom fit. And well, in order to fix this issue, well, why do I have a... Okay, let's go to the window, and for the t step, so what we're going to do for the theta step, we're going to ask the calculator to plot more points by having these steps to be smaller steps, 0.005, and it's going to take some time. Well, right, and we get this. Well, it actually didn't give us the entire graph, so it looks like two loops here, and all right, so that's one graph, and the other graph is r equals to the square root of 2. So essentially this function r equals the square root of 2, it's telling us something that has a radius of square root of 2. It's just a circle, isn't it? So it's going to be this circle right here. All right. Now they're asking us for, okay, again. Nope, not eraser. The area outside of the circle, but inside of the Leibniz gate, but rather only in the first and fourth quadrants, which is essentially only this area. All right. But now we need to figure out these angles right here. So, however, in order to find these angles, we need to find the points of intersection between that circle and that Leibniz gate. So we need to find those angles. In other words, those rays. So let me draw this as a couple of rays where these two intersect. That way we get a better idea of what are we really finding. So in other words, we need to set these two quantities equal to each other. That is, for cosine 2 theta, where is that equal to the square root of 2? So that's the square root of that. So square both sides. That's going to give us 4 cosine 2 theta equals to 2, and cosine 2 theta equals to 2 over 4, which is 1/2. So now we're looking for all the value, or for all the angles for which cosine is it's 1/2. So 2 theta is going to be for angles like pi over 3, 5 pi over 3, but theta should be pi over 6 and 5 pi over 6. All right, which I think this makes sense, right? Because this is the pi over 6 right here, and well, this negative angle, which could be negative pi over 6, it's also pi over 6. All right. So 5 pi over 6, let's call it 5 pi over 6, and also let's name it negative pi over 6, which is essentially the same value, isn't it? All right. So again, look at the shape of this area that we want to find. So we have the same area above and below. If we compute this integral with these limits of integration, most likely we're going to get a 0 value. And again, that doesn't make sense because, well, unless my eyes are deceiving me, well, I'm seeing some area which is not 0. So let's write down this integral. So that'll be the area, the double integral of r dr d theta. Again, that invisible one implies that we're finding area, but now the radius varies the outermost point by 2 square root of cosine 2 theta, and the innermost point is the points on the circle of radius square root of 2, while the angle, well, on the one hand we can say from negative pi over 6 to pi over 6. However, if we can turn this into a 0 and just multiply this by 2. All right? And well, in this case, they're not asking us to compute the value of the integral, only to write the integral, to set up an integral, all right? So, no, so here is the thing.